Yeah.
Just for the question where we're doing the cylindrical coordinates for
Separation variables. Yeah.
For I think
Yep.
yeah, for Laplace equation.
Yeah.
I just don't know how to set up the boundary condition. Like, is it still between two plates with a zero and then a cylinder in the center, or is it like a cylinder of zero?
So it is here. Why don't we let's take a look at what it
Because
is.
in class we did like two plates at zero and then a plate between.
Yeah. I just want to see the problem so I don't say anything that's not accurate. So consider an infinitely long cylinder of radius r and okay, so we're looking at finding the potential only inside the cylinder. We're not worried about
question one.
question one. Oh, okay. Oh, sorry, you're doing the
in cylindrical coordinates.
Fine. Oh, okay.
And so when we did in class, we had like the two plates at zero and then the plate between.
But that was a specific example, right? This first question, you don't need to know anything about the geometry of the problem. You're just trying to. Oh, there's a marker.
So you just get it just with the general form, not solve for the
Yeah, question two gives a specific case, right? So what you want to do is you want to solve del squared v in cylindrical coordinates, and so I don't remember exactly what it looks like, but it's something like yes, s times d ds, something like that, plus 1 over s squared g by d phi squared, and then we're going to ignore the z part, right? Is this right?
Yeah.
Right, and then you're going to put v is s times phi, right?
Yeah.
Okay, so you put that in there. So you're gonna, this is gonna come in s, and then you're gonna get a phi here, and then here you're gonna get an s and a phi. And then you're just gonna divide by s times phi, so you get capital S here, capital phi here, And so you want this to be 0, right?
Yes.
And so now you just say this is gonna be, in fact, if we multiply by s squared first, that would be better.
Yeah.
Because then you're gonna get a 1 here and an s here. And so now you're gonna say this one is k squared and this one's minus k squared. And so the minus k squared one should be similar to what we've done, that should result in the trig function. And then this one is where you have to find the solution for capital S.
Right, okay,
Yeah.
so then once we get in a form where it has 4 constants, then.
That's done, yeah. You're gonna find those constants for an example.
Okay, okay, thank you.
That's assignment 2.
We could have grabbed lost clause. I think a lot of us forgot.
I think I basically just didn't put them out. I had them, the TA gave them to me, but I never really offered them to you.
I got it on. I got it on. Okay.
Okay, so I think we'll get started. What we were discussing last time was we kind of relaxed this requirement that our source charges would be stationary. And so what we found is when we allowed our source charges to move, they did some funny things. First, they created magnetic fields, and we kind of figured that out by imagining placing like a little compass next to, say, a wire carrying a current. And we found that the magnetic field kind of loops around that current. And then we also found that the moving charges experience a force when they move, when they have a component of their velocity that is perpendicular to an external magnetic field. And then we saw a little demo where we induced circular motion of electrons in like a little vacuum tube that's been filled with neon gas. And so the excited neon gas shows us the path that the electrons followed. All of this, we could summarize that for a charge in a region of space with both an electric and a magnetic field, the net force on it would be given by this expression. The examples we did last time imagined only a charge moving in a magnetic field. I want to do kind of think about a fun example that gives rise to surprising motion, where we allow both an electric and magnetic fields that are non-zero. And so the problem that we want to think about is this one. So we want to consider a particle that's at rest. And so here it is. I put a charged particle, Q is positive. It's sitting at rest at the origin of this coordinate system. And the region of space that this charge lives in has a constant electric field along the z-axis, and then perpendicular to that, we have a magnetic field along the x-axis. Now, I've drawn only one electric field vector and only one magnetic field vector, but what I'm imagining is that this electric and magnetic fields, they're uniform throughout this entire space, okay? We're not going to solve this problem mathematically. I want to see if we can understand the behavior qualitatively. So let's see if we can do that. So we will examine the resulting motion of the charge qualitatively B. C. Griffiths example 5.2 for a quantitative analysis. What I'm more interested in at this point is not really writing down differential equations and solving them. It's just understanding kind of the unusual behavior that we're going to observe. So here's the picture. We're going to start with Q at rest at the origin. And let me just write down here our force equation once again. It's QE plus V cross B. Okay. All right. So let's see if we can get started. So I'm going to draw this again, but I'm going to make it a little bit bigger, and I'm going to draw just the X, Y plane. So here's our Y-axis. We have a magnetic field that's coming out of the screen, and so I'll draw it like so. And then we have our electric field going up the Z-axis. Okay, and we start with our charge sitting at the origin at rest. So what's going to happen first? What will happen to this charge? What force will it experience? Yeah, just the electric force. The magnetic force will be 0. Why is it 0? Yeah, because the magnetic force is V cross B, and if we start at rest, V is 0, and so it's not moving. So the only force acting on our charge at this moment is the electric force, and so we'll indicate that like so. Okay. Well, what happens is the electric force causes the charge to accelerate upwards, and so if we wait a short time, our charge will end up over here, roughly. Okay, so let's say this is time t0, and this is some later time t1. All right. So now the velocity of our charge is something like this. So it has some velocity like so. All right. Now, throughout this entire analysis, since the electric field exerts a force that's just Q times E, the electric force is going to be constant all the time. That's never going to change. It's only the magnetic force that's going to be changing. So what direction will the magnetic force be in this case? The velocity is up and the magnetic field is coming out of the screen.
Positive Y.
Yeah, okay, so it's going to be V and then cross B. So B is this direction. And so my thumb points to the right. So what we're going to have is we're going to have the electric force that never changes. And now we're going to have a magnetic force that is something like this. I'll draw the magnetic force small just because right now we're imagining our charge is moving slowly because it's just started from rest. And so the net force is something like this. All right. So that's going to cause the charge to move along this trajectory, and it ends up something like over here. Now, this charge is still sort of has a component of its motion that's in the direction of the electric field. So is it going to be speeding up, staying the same speed, or slowing down? It should speed up. So it should be moving faster. Its direction of its velocity will be sort of tangent to whatever curve it's following. So there's its velocity. Now the electric force doesn't change. Whoops. My forces are in green. My electric force doesn't change. The magnetic force, what is the direction of the magnetic force now? Well, it's gonna be V cross B, it's just perpendicular to this orange arrow, but the velocity is a little bit faster now. And so now we're gonna have a magnetic force that's a little bit stronger, something like this. And if I add these two vectors, what do I get? You know, something that's a little bit horizontal. So if the net force is now horizontal, our charge is gonna follow some kind of path like this. So, and then it ends up over here. All right. So then, what are we gonna have? We're gonna have a velocity that's in this direction, like so. It might have sped up a little bit, but if this net force is in this direction, there's still a component that's kind of in the direction of the velocity. So maybe the velocity changes a little bit, but it's sort of not changing so much anymore. The electric force is in this direction. The magnetic force is going to be opposite of that. And it'll be stronger because the particle's moving fast. And so now the net force is downwards, and our particle starts following this sort of path. Now it's moving against the electric field. So its velocity has a component that is against the electric field. The electric field starts doing negative work. So it's losing kinetic energy, it's losing speed, and our particle will start to slow down. Okay, so it slows down. So from here to here, I would say we have speeding up. And then over here, we're going to have slowing down. And you can already see this is different than the example of uniform circular motion, because in that case, we were going around the circle at a constant speed. That's not what's happening here. Okay, so this is going to follow a path like so. Let's just go all the way down here. What do you suppose oh, I didn't draw my forces. So here's my force, and here's my magnetic force would be something like this. And so now my net force is, I don't know, something like better than that. My net force will be something like this. Okay. How fast do you think our charge is going to be going when it hits this y-axis? And not moving at all. And how could we argue that? Well, the work done by the electric field is positive when the displacement is in the direction of the magnetic field. So we get a certain amount of positive work, which causes the charge to speed up. But then we get an equal amount of negative work on the way back, where we're going against the electric field over the same distance. And so the total work from here to here by the electric field is 0. So no change in speed. If this started at rest, this will end at rest. What about the magnetic field? How much work does the magnetic force do? 0 all the time, right? And so here we would get V is equal to 0 at this point. And then the whole process would repeat because we're now at the same starting position as we were before. We moved along the y-axis a little bit, but what will happen is because this electric field is uniform, same everywhere, it'll start accelerating up again, and we'll get this funny type of motion where it would follow this kind of path. And so our charge is doing this funny thing where we started at rest, and its motion is perpendicular to both the magnetic field and the electric field. Okay, this motion of Q is perpendicular to both E and B, and we get a displacement along the y-axis. So you can see already where we get sort of a pretty simple situation. Just put a charge at rest in a perpendicular electric and magnetic field, and we already get some non-intuitive sort of resulting complex motion out of that. Yeah. Yeah, as long as the electric and magnetic fields are uniform, like as long as E doesn't go away and B doesn't go away, we just hop along this y-axis forever indefinitely. Yeah, and the exact shape of this is a cycloid. What's a cycloid? Who remembers?
Like, put a pencil on the wheel.
Yeah, that's right. So let's see, I might even be able to find a crappy GIF. Here it is. So there's the cycloid motion. You imagine a circle rolling along this axis, and you pick a point on that circumference of that circle, and that point traces out the cycloid. Right now it's at rest, and then it starts moving, and it's moving fastest when it's at this peak here. So that's the cycloid motion. All right, good. So when I first saw that in some math class, I thought, well, that's cute, but I don't know if it has any real relevance. Evidently it does. Okay. All right. So 5.1.3, I'm going to start talking about current. So a lot of this I think you will have seen before. So current is the charge per unit time crossing a surface. So let's imagine a wire. It's going to be filled with some mobile electrons. And so we can draw some of those electrons. And so let's imagine that we do have a flow of charge. And so we've got some charges moving along this wire. The way we would establish that flow of charge is we'd have to have some potential difference between the two ends of our wire. And then I imagine just taking a surface and having our wire pass through that surface. So maybe there's a little circular cross section of that wire. And we sit there with a stopwatch and we say, okay, I'm going to time, a certain time interval delta t. I'll count the number of electrons n that cross that surface. The total charge will be n times E. Divide that by the time interval delta t. That's the definition of current. So if total charge delta Q crosses our surface in time delta T, then the average current would be equal to delta Q over delta T, and the instantaneous current would be the limit that delta T goes to 0 of that ratio, which is just the derivative dq dt. All right. So I want to be able to express this in terms of other quantities. And so what I want to imagine now is that our wire has a certain density of mobile electrons. So if our wire has a free/mobile charge density, I'm going to say rho is going to be E times N. Okay, so E is going to be the charge of an electron, or the fundamental charge, and N is the number of electrons per unit volume. Okay, so if I took n and multiplied by, say, mass, I would get a mass density. If I take this little n and multiply by charge, I get a charge density. Okay, so if I wanted to, then I could say, well, look, usually when I have wires, I like to talk about the charge per unit length. So I could say lambda is charge per unit length. And what I'm going to do is I'm going to multiply by area over area, where my area represents the cross-sectional area of my wire. So length times area is going to be the volume of my wire. So now I have QA over the volume. But Q divided by the volume is going to be the charge density, rho charge per unit volume, charge per unit volume times A. And so we get the result that I wanted. Lambda is rho times A, and that's the same as the amount of charge per unit length. Okay. Well, what I want to do is I want to write lambda V, lambda times the speed of a charge is going to be equal to what? Delta Q times delta X. And what's another way of writing the speed? It's the displacement, delta X, divided by delta T. And so this is delta X cancels. This thing is just the speed. Well, what are we left with then? Delta Q over delta T, but that's just current. And so therefore, our current, which is dQ dt, can also be expressed as lambda times V, which is also lambda is rho times A. So this is also rho times A times V. And rho we wrote as the electron charge times the charge for the number of charges per unit volume, and E times N times A times V. And so you may have seen this, you may remember this expression from like a first year class. What was the speed usually called? Do you remember? It's how fast the charges are moving along our wire. Yeah, it's current density is J. So if I divide by the area, that would be my current density. This is called the drift velocity. So this was the drift velocity. Okay, right. All right. So if we want, we can define the current as a vector. So it's either going to be moving to the right in our wire or to the left. And so we could say I is equal to lambda times the velocity vector. So just using this relationship where the current is in the direction of the motion of the charges. Okay, so what I want to do then is last time we wrote down the force on a charge moving through a magnetic field. Very often when we have motion of charge, it's a collection of charges moving together as a current. So what we're going to do is we're going to try to write down the force on a segment of wire of length dl in a magnetic field B. Okay, we'll start with a picture. So this is some wire of some arbitrary shape. And I'm going to pick a certain segment of this wire, something like this. It has a length of DL. And inside this little segment of wire, there's a total charge dq. So if we knew the volume of this segment, we could multiply by the charge density, and that would tell us the total charge. Okay, and then we suppose that there's some magnetic field at the position of this little segment B. Okay, so let's imagine that the current in our wire is flowing left to right. The charge is flowing left to right. Then what we know about a charge moving with some velocity v along the direction of the wire, then if I curl my fingers into the direction of the magnetic field, my thumb points into the screen, so there must be a magnetic force into the screen in this case. So we would have F magnetic would be into the screen by the right hand rule. Okay, so let's go ahead and see if we could work out quantitatively what the force will be. So this is the force on segment DL. So it was Q times V cross B. So let's see if we could work that out. It's going to be dq, whatever that is, times V cross B. Well, let's see, dq, well, if we have a charge per unit length, and we know that the length is dl, then I can take my charge per unit length, multiply by dl, that tells me how much charge I have. Okay, so then what we could do is we could write this as lambda times V cross B and then dl. So this lambda times dl is the dq. I've just grouped the lambda and V together because we just defined lambda times V to be this current, the vector version of the current. And so this is I. And so therefore, the magnetic force on this little segment is going to be I cross B times dl. And if I wanted the total force along the entire wire, I would do this for each of the little segments and then add them up vectorially, which is equivalent to saying the magnetic force on our wire is equal to the integral of I cross B dl. Okay. Now, in a lot of textbooks, they will define the current to be a scalar quantity, and they'll associate the direction with this dl, this little step along the wire. Because they're in the same direction, it's often conventional. It is conventional to write I as a scalar and assign the direction to dl. So dl is going to go to dl vector, and the direction of the dl vector has to be in the direction of the current. I personally, I like this version better, but what you'll often see written is that the magnetic force on our current carrying wire would be the integral of I times dl cross B. And so that's an equivalent expression. This one has, it's a bit unusual to see, like usually people like to put the dl at the end, but nevertheless, here we go. I guess you could put it at the end if you wanted to, you could do B cross DL, then you need a negative sign. All right. Good. So what I want to do is, I want to generalize this. So instead of thinking of just a kind of current along a sort of one-dimensional wire, we can generalize to higher dimensions. So we can generalize this result to the case of a charge flow over a surface. Okay, so what's that going to look like? So let's draw some kind of surface. So this could be either like a thin sheet that has a current flowing off over it, or it could be like the boundary of some volume or something where there's some charge on that surface of whatever that bounding volume is enclosing. Okay, so we're going to have a surface current density, and we're going to call that K. So K is the surface current density. And so what we'd like to do is figure out what are the analogous relationships for the surface current density. The way we're going to do it is, let's imagine we take this surface and we cut it up into little ribbons. And then each ribbon is kind of like a wire that's side by side. And so we already know a little bit about how to deal with currents in wires. So we'll make this thickness DL, and I'm going to call it DL perpendicular, just to emphasize that we've chosen our ribbon such that it is parallel to this surface current density. All right. So we consider a ribbon of width DL perpendicular that is parallel to the charge flow. The ribbon carries current DI is K times DL perpendicular. All right, so this is going to be like some charge per unit length, and then if we multiply charge per unit width, if you like, and then if we multiply the width of our ribbon, that's how much current is in this ribbon. Okay. So that means then, of course, it's equivalent to write that the surface current density is the charge per unit width. Sorry, the current per unit width. So this is the current per unit width. Okay. Well, we already know a little bit about currents in wires. We said that the current in a wire is lambda times however fast those charges are moving. Okay, well, lambda is dq dx, the charge per unit length, times velocity. So what I want to do is I want to just substitute this thing into here, and we could say our surface current density is going to be di, which is dq divided by dx times v. And then we have to divide by this dl perpendicular. dl perpendicular. But dx is how far we move along the wire. And dl perpendicular is the width of our wire. So the product of the two gives the area of that wire. And so this is dq dA times v, where dA is dx, dl perpendicular is the wire area. All right. But if dq by dx was the charge per unit length, then dq by dA is the charge per unit area, which we usually denote by sigma. And so sigma times v is the charge per unit area is sigma times v gives us the surface current density. So it's kind of nice because now we have, for our one-dimensional wire, we had that I was equal to lambda v. And now that we have our two-dimensional surface, the surface charge density is sigma times v. So in that way, it's kind of nice and analogous. Okay. Right. So then if we were to do this force calculation for our surface charge density, we want to do the same sort of analysis we did before. We'll start with dq, v cross b, and see where it leads us. So therefore, the force on our surface current would be, well, F magnetic is always dq v cross b. Let's say this is the force just on a small piece of our surface that has charge dq. All right, well, we know that dq is going to be sigma dA. Okay, so dq times v is going to be sigma v times dA. And so we could substitute that in. So dq times v is going to be sigma v cross b, and then we had a dA, like so. But this sigma v is the same as k. And then if we integrate so that we add up the forces on all the little patches that make up our surface, we find the magnetic force is equal to sigma v cross b dA, which is the same thing as the integral of k cross b dA. So this is just the extension of the 1D wire version results that we had. All right. So I want to finish this off, we'll extend it a little bit further. So instead of a charge flow over a sheet, what if we had charge flow through a volume? So finally, we can have a current distributed throughout a volume. All right, so let's imagine we had like some fat wire, it doesn't even have to have a uniform shape. And then we put in here some kind of little rod that goes through our wire. And this rod is going to be parallel to the flow of charge through this volume. Okay, so you already mentioned, or it already came up, that we have the possibility of having a current density J. And so this is what we imagine we have now, a current per unit area flowing through this volume. All right. I'm gonna take this and I'm gonna say this is dA perpendicular, just like we had a DL perpendicular, the width on our sheet. Now we have this area on our volume, and perpendicular just means that this J is flowing through that surface perpendicularly. Okay. Good. So now DI is going to be equal to J dA perpendicular, and I'm going to call this number sign. We're going to come back to it. Okay, so what does that mean? J is equal to DI divided by dA perpendicular. So just dividing by dA. I is lambda V, dA perpendicular. Lambda is dq dx, just doing all the same stuff we did for the sheet case, dA perpendicular. So now ds is a step along this rectangular section. And so if I have dA perpendicular, I take a small step, I define some volume. And so this is dq d tau times the velocity, where d tau is equal to dA perpendicular, dx is an infinitesimal volume. Okay. But charge per unit volume is just the charge density. So dq d tau is equal to rho is the charge density. All right. So what does that mean? F magnetic on a small piece of this little wire that goes through our larger volume is going to be dq V cross B. And we want to write dq as, well, let's see. dq is going to be, I should have done it where, so dq is equal to rho d tau. Okay. So then dq times v is equal to rho v times d tau. And we're going to substitute that into here. And what are we going to get? We're going to get a rho v cross b times d tau. But rho times v, this is rho here times v. It's just the same thing as our current density. So this is rho. And so this is equal to the current density J cross B tau. And so therefore, F magnetic is again given by the same sort of structure. The only thing that changes, are we thinking about a one-dimensional current, a current flowing over a sheet, or a current flowing throughout some volume? All right, so all of this stuff just arises from what we were calling one of the axioms of magnetostatics, let's say, and that's the Lorentz force law, right? We always start with the Lorentz force law, which I would have written down somewhere right there, and then we kind of generalize it to whatever geometry we happen to be using. Okay. So we labeled a particular equation number sign here. So I want to return to this expression. So let's return to number sign, which said that di was j dA perpendicular. And so let's see if we can kind of generalize this idea a little bit. I'm going to draw another sort of volume that's going to be carrying some kind of current density. And what I'm going to do is I'm going to define a cross-sectional area. Maybe I'm going to try to draw it better than that. I'm going to define a cross-sectional area, but it's not perpendicular to the axis of this cylinder, right? So it's going to be, if I put a normal vector, it'll be something like this. And so what I'm going to do is I'm going to say dA is equal to whatever that area is times that normal vector. Okay, and then we imagine that we have our current density in here, it's flowing in this direction. What we could do is we could take the dot product of this J and this dA vector, and it's going to select the part of that surface that is perpendicular to J. And this will have the area A perpendicular, dA perpendicular. Okay, and this is just equal to dA dotted with the direction of J. Okay, well, that means then if we took J dot dA, that's going to be the same thing as J dA perpendicular. And we said that this is a current per unit volume, right? It was dQ divided by d tau. Sorry, no, current per unit area. Let's see, where did we write that down? Here it is, current per unit area. So the total current crossing a surface with area dA is, well, it would be the integral of J dA perpendicular, but we've just said that we could write that as J dot dA in general. All right, so what I'm thinking of right now is just like a little piece of area that's a cross section of some, I don't know, bulk wire. But we could also ask a question like, let's make a surface that bounds some volume. So a closed surface that encloses a volume. And we can ask the question, how much current crosses that bounding surface? And that's equivalent to asking how much current is flowing out of our volume. And so let's see what happens if we do that. So for a closed surface that bounds a volume, I'm going to try to write some volume as a script V through which J flows. The current crossing or exiting that bounding surface is, oh, let's do maybe not a bracket, let's do just a slash. So a current is either crossing or exiting that bounding surface is given by, well, it's this exact expression that we wrote down, it's just that our surface is not like a plane, it's now a closed surface. And so we could write that as an integral over a closed surface of J dot dA. Okay, and we'll call this surface S. So current that's exiting our volume. Okay, when you see something like this, it should start ringing bells and alarms and things. What can we use when we have a surface integral with a dot product and we have a closed surface? What's that? No, yeah, it's not Gauss's law. You're right. So if this was E dot dA, what could we do with this? We could use, there's a theorem, divergence theorem, that's right. So let's apply the divergence theorem, which says we're going to take the divergence of J and integrate over the volume. So that's where my script V comes in. Divergence of J over some volume, and this is from the divergence theorem. Okay. So there it is. Well, if our current is exiting our volume, the reason I use exiting is because when we define a closed surface, the dA vector is always pointing out. And if I want the J dot dA, positive results of that dot product will be the flow of charge out of our volume. So that's why we keep saying exiting. So if current is exiting our volume, we're losing charge at a rate of minus dq dt, right? dq dt is the current, but because current is leaving our volume, the total charge inside our volume is going down. So dq is negative. All right, so what does that mean? That means that this divergence of J d tau is minus d by dt of q. If I had a volume that was charged, how would I calculate the total charge in that volume? If I suppose I told you what the charge per unit volume was. Yeah, so I mean, what we would do is we would say minus d by dt, that part I'm not going to change, but q I could write as rho d tau, right? So this is just another way of writing the total charge in our volume. Total charge in our volume V. All right. Well, let me take this a little bit further. I'm going to take the minus d by dt inside, and so we would have minus d rho dt, and then d tau. And what I want to do is I want to compare these two. It's the exact same integral, and they have to be equal to each other. So that's only possible if the divergence of J is equal to this minus d rho dt. And so therefore, this is the result we wanted to get. Minus d rho dt. This is a statement about charge conservation, right? Because we imagine we have some charge per unit volume, or sorry, charge per unit area flowing throughout our volume. Some of that charge may exit our volume. If it does, there must be a corresponding change in the charge density of that object. Okay, so this is a statement about the conservation of charge. And it has a name. It is called the continuity equation. All right. There's a special case of this, and the special case corresponds to a steady current. And so by steady current, what we're going to mean is I have some wire that has some volume. Maybe we have some current flowing in that wire, and maybe it's true that some current is exiting the bounding surface. But by steady current, what we mean is that if I have a certain amount of charge exiting at one position in my wire, there's going to be an equivalent amount of charge coming in at a different position, and that will maintain a constant charge density. And so in that case, the divergence of J would have to be equal to 0. So a steady current is defined as a current which is constant. The only way you could have a constant current is if you keep replenishing the charge, because if I wasn't replenishing the charge, then if I have a current flowing and it keeps exiting my volume, eventually that volume is going to be depleted of all of its mobile charge, and it can't possibly maintain that steady current. Okay, so any charge exiting a volume is replenished by an equal inward flow of charge. This corresponds to d rho of dt equal to 0, and that is what we're going to mean by magnetostatics. So electrostatics was no motion of charge. Magnetostatics is kind of a steady current. So there's motion of charge, but any charge that's lost through some volume has to be replenished by some inward flow at some other point. Okay, so in magnetostatics, then the continuity equation becomes the divergence of J is equal to 0. All right, so that was one of the results that I wanted to get. I want to do one other thing. I was going to do an example as well, but we may not be able to do that example today. We'll see. All right. So far, the only thing that we've talked about quantitatively is about the forces on moving charge or current in a magnetic field. We also know that this moving charge creates magnetic fields, but we haven't written down how to calculate that yet. And we're going to get that from the so-called Biot-Savart law. This is another one of those expressions that's not going to be derived from anything, but it's going to come from experimental observation. So what this does is it describes the magnetic field that's generated by a steady current. So it is an empirical equation based on experimental observations. In the same way, for example, that Coulomb's law was based off of experimental observations. We didn't derive Coulomb's law, we just wrote it down. Okay, so how could you do such an experiment? You could imagine taking a wire, putting a current through it, and like we talked about last time, you could get the direction of the magnetic field using a compass and placing it around this current carrying wire, and you would find that the magnetic fields loop around these currents, and the direction is given by the right-hand rule. And then you could contrive some kind of way of measuring the torque on this needle, like how strongly is the magnetic field holding your compass needle in that fixed orientation. And that would tell you the strength of the magnetic field. And if you did all those things, you would find that the magnetic field at some position R is given by a constant. This is a constant of proportionality. We're going to call it mu naught over 4 pi. But that's not the interesting part. The interesting part is that it's going to involve a cross product, just like the force did. And it's going to be proportional to 1 over the square of the script R. And the last little bit is we have to do a dl prime integral. So let me draw a picture so I can label some of these things. So I think what we'll do is we'll draw a coordinate system over here. So let's say X, Y, Z. So here's our origin. I'm going to draw a little loop of wire that lives in this space. Something like that. And maybe, well, in fact, I'm going to change that. I'm going to draw a little section of wire that lives in this space. In practice, the section of wire would have to eventually form some kind of closed loop if we're going to sustain a steady current. But what we could do is, let's say, just for fun, that current is going in this direction, for example, and we're going to say that this is going to be our dl prime. This is a little segment of our wire. And I want to label the variables that were in this expression here. So just like we did for electrostatics, we're going to use R prime to indicate the position of our source. In this case, the source of our magnetic field will be this little section of our current carrying wire. And then I want to know what the magnetic field is at some other point P, and this vector R tells us where point P sits. And then script R connects R prime and R. So specifically, script R is equal to R minus R prime. This is the vector from the origin to our source. And this is the vector from the origin to our observation point, P. And this is the vector that goes from source to P. All right. This cross product is the one that tells us that the magnetic field is looping around the current. This 1 over script R squared says that the strength of the magnetic field falls off as 1 over the square of the distance from source to observation point. Let's see if we were to draw the magnetic field. So our current velocity is in this direction, and then we have to cross with script R. Script R is kind of pointing up. and my thumb points into the screen. So at point P, we have a magnetic field that's going into the screen at P. Okay, the factor of the current tells us that what we would have to do is if we double the current, we'd get double the magnetic field. So the field is proportional to the strength of the current. And then this DL prime says that this is all due to just the little segment DL prime. If we add up all the contributions from all the DL primes, we do that by integrating. Now we get the magnetic field that's due to the entire wire. All right. How are we doing here? Oh, we got a bit of time. So let's see if we can do an example. This is a little abstract. So let's see if we could do an example. Let's find the magnetic field due to a long, straight wire. All right. So let's make it easy. We'll just make our current be running horizontally in this long, straight wire. We'll work in cylindrical coordinates. And we'll say, okay, let's put over here, this will be our DL prime. And what we need is the vector from our source to our observation point P, like so. This will be script R. And so if I want to, I could also put in this unit vector script R hat. So one of the things that we need to do is we need to do the cross product of the current and the script R hat. Okay, well, the current in this case is off to the right. Script R hat is kind of pointed up at that angle. My thumb points out of the screen. So in this case, our magnetic field is coming out of the screen at point P. All right. In cylindrical coordinates, we have this parameter S, which is the perpendicular distance from our axis to whatever our observation point is. And the last thing I'll label on here is theta. So some of the things that will be useful for us is the sine of theta is the opposite over the hypotenuse. And so that's S over the length of script R. What we'll do is we'll say that the distance from, or the base, we'll make a right angle triangle, and we'll say the base of our right angle triangle is L prime. Okay, so that means script R is S squared plus L prime squared all square roots. So this is S square root of S squared plus L prime squared. Okay, so I think we're ready to start to try to apply the Biot-Savart law. So we have mu naught over 4 pi. All right, and then we had the integral of I cross R hat over R hat squared. So we'll just write it down. I cross R hat over R hat squared DL prime. All right. Let's see. I cross R hat is the magnitude of I, which is just I, times the magnitude of a unit. What's the magnitude of a unit vector? 1. And so then we have sine theta. But we already just said that sine theta was S over the square root of S squared plus L prime squared all square root. So this is a vector B bar is mu naught over 4 pi, the integral. So the cross product gives us this little mess here. And then we have to divide by script r squared. But that was the hypotenuse of our right angle triangle. So it's s squared times L prime squared. And then we have dl prime. If our current is constant, we would have, for magnetostatics, it will be. So mu naught I divided by 4 pi. And then we have the integral of s over s squared plus L prime squared. This is all to the 3/2 power now.
And cross square means that
Uh,
the square root s squared plus, oh no, sorry, that's square.
yeah, so yeah, this one times this one gives that 3/2 power. I think that's okay. Now, if this is a really long wire, our limits of integration will be plus or minus infinity. So this is for a long wire. Okay, and then I'm not going to do the integral, but this is one of those trig function substitutions. So I think this is the one where you would substitute L prime as something like s times tan of alpha or something like that. And if you go do that, or if you look up the integral, what it's going to be is mu naught I s divided by 4 pi, and then you end up with an L prime s squared plus L prime squared. And then this is from L prime is equal to minus infinity to plus infinity. Well, let's see what that's going to do, because we're going to end up with infinity. Let's do the upper integration limit. We'll get infinity divided by s squared plus infinity squared. Well, that's just going to be infinity squared. Take the square root, it's infinity. So it's the infinity from L prime divided by the infinity from L prime. It's going to be a +1 factor. So that's going to be mu naught I s over 4 pi. I'll put the s squared over here. And then we would get 1 minus. What are we going to get when we put in the minus infinity? Yeah, we're going to get a 1 again, but what's the sign of it? Minus, right? Because the minus infinity in here is going to be squared. So it becomes positive, and then take the square root and take the positive root. So we get an L prime here, absolute value. So at minus infinity becomes plus infinity. And over here, we just get a minus infinity. So the ratio is -1. So we get a -1 like so. Okay, so that's good. Cancel the s's. 1 minus -1 is a 2. And so B is equal to mu naught I over 2 pi s. And what should we do for the direction? In cylindrical coordinates, we know that we're going to get magnetic fields that loop around like so. So what's the direction in cylindrical coordinates? Theta hat, right? So theta hat is curling around in this direction. And so yeah, you're exactly right. This is just the theta hat direction. So maybe what I should do is over here, I drop the vector notation. So let's just say we're trying to find the magnitude of this right now. And so the direction of B in cylindrical coordinates is theta hat. And so B is equal to mu naught I over 2 pi s. Is it I think they use phi, right? They use phi in cylindrical coordinates, I think. Is that right? Okay, good. So what I want to take away from this is that that was kind of a difficult calculation using the Biot-Savart law. And generally it will be, you have to, it's a vector calculation, it involves cross products, there's the script R, so you have to work out the geometry. And even when you do all of that, we end up with kind of a nasty integral, even for what's probably the simplest case we could write down, the simplest possible current. So we'll spend some time in this chapter trying to develop alternative ways of calculating magnetic fields. For electric fields, we had Gauss's law, which worked in situations where there's a high degree of symmetry. For magnetic fields, we're going to have Ampere's law, which also works in the case where you have a high degree of symmetry. So you're going to have either cylindrical geometry or like charge distributed over a sheet or something like that. Okay, good. So I think with that, that's where we'll stop today, and we'll pick this up next week. All right, thanks everyone. Yeah.